Imagine a star that is not really a star. It shines with the power of 100 billion suns, yet at its heart may be a black hole feeding on the very gas that surrounds it. Astronomers now think they have found a new kind of cosmic object, a black hole star, a strange hybrid that could explain one of the deepest mysteries revealed by the James Webb Space Telescope. The discovery is exciting because it sits at the intersection of two extreme ideas. A black hole is usually defined by what it destroys, while a star is defined by the nuclear fire it creates. But in the early universe, those categories may have overlapped. In this episode, we will travel more than 13 billion years into the past. We will see what Webb actually observed, why the object looks like a star, how a black hole could power it, and what this may tell us about the mysterious little red dots appearing in the telescope's deepest images. Start with the name. A black hole star is not a black hole wearing a glowing shell in the simple science fiction sense. It is a proposed system in which a rapidly growing black hole is buried inside a dense cocoon of gas, dust, and radiation. The black hole itself gives off no visible light. But as gas spirals inward, it forms a hot accretion disk. Friction and magnetic fields heat that disk to incredible temperatures, causing it to shine across the electromagnetic spectrum. If the surrounding gas is thick enough, the entire system can appear from far away as one compact, brilliant object. That appearance is the key. At the enormous distances involved, Webb cannot see the central black hole directly. It sees a tiny source of infrared light. The light has traveled for billions of years, stretching into longer wavelengths as the universe expanded. The object highlighted in recent reports is especially interesting because it is extremely distant and extraordinarily bright. Estimates suggest that its total luminosity may reach roughly 100 billion times that of the Sun. Yet the light does not behave exactly like the light from a normal population of stars. Instead, its spectrum carries clues of intense, energetic activity. Some wavelengths appear unusually strong, while others are suppressed. That pattern can be produced when powerful radiation from a central black hole strikes the gas around it, ionizing atoms and creating a glowing envelope. Think of it as a cosmic lighthouse inside a fog bank. We do not see the lamp itself. We see the fog lighting up, and by studying the colors and timing of that glow, we infer what kind of engine is hidden within. Why is this surprising? Because the object exists when the universe was still very young. The first galaxies had only recently begun assembling. There should not have been enough time for ordinary stellar evolution to create enormous black holes through the slow processes we observe nearby. This is one of the biggest puzzles in modern astronomy. Webb has found compact, red sources in the early universe that appear brighter and more mature than expected. They are often called little red dots. Some look like miniature galaxies, some resemble active galactic nuclei, and some may be something in between. The black hole star idea offers a possible bridge. In one version of the scenario, the first stars were unusually massive because the early universe contained almost no heavy elements. With little metal to help gas cool and fragment, a giant cloud could collapse into a single enormous object. That object might begin life as a supermassive star. At its center, gravity would eventually win. A black hole would form, but the outer layers could continue to surround it. The newborn black hole would then feed on the remaining envelope, releasing energy and helping support the outer gas. For a short but spectacular period, the result could look like a star powered partly by nuclear fusion and partly by accretion. It would be massive, unstable, and far brighter than ordinary stars. Eventually the envelope could be blown away, leaving behind a large seed black hole. This matters because seed black holes are the starting points for the monsters at the centers of galaxies. Today, astronomers see black holes with millions or billions of solar masses. The problem is explaining how they became so large so quickly after the Big Bang. A black hole born inside a supermassive star would begin with a head start. It would not need to grow from the remnant of one ordinary star. It could start with thousands, perhaps tens of thousands, of solar masses and then continue feeding in a dense environment. The idea is not proven. Astronomy rarely advances from one spectacular image to certainty. Instead, researchers compare predictions with multiple observations. Does the object have the right color? Does its spectrum contain the expected emission lines? Does its size make sense? Does the surrounding galaxy show signs of an active nucleus? Webb is powerful because it combines sharp imaging with spectroscopy. Imaging tells us where the light is and how compact it appears. Spectroscopy spreads the light into its component wavelengths, revealing the chemical fingerprints of the gas and the energetic processes shaping it. The red color is important, but it does not automatically mean the source is ancient or unusual. Cosmic expansion shifts light toward the red and infrared, while dust can also absorb blue light more efficiently than red light. A convincing explanation must account for both effects at once. There is another challenge: distant objects can be blended together. A black hole star, a young galaxy, and a small group of galaxies may appear as one point in a telescope image. Higher resolution observations and careful modeling are required to separate the possibilities. That is why this discovery is best understood as a clue, not a final answer. It may be one member of a population that astronomers have only just begun to recognize. Or it may represent a rare phase in the life of early black holes. If black hole stars were common, they could solve several problems at once. They could explain why some early sources are so bright, why their spectra look unlike simple stellar populations, and how massive black hole seeds formed before galaxies had time to mature. But nature may choose several routes. Black holes might also grow through direct collapse of gas clouds, through repeated mergers, or through episodes of super-Eddington accretion, in which matter falls inward faster than standard theory allows. The little red dots could therefore be a mixed population. Some may be young galaxies packed with stars. Some may be active black holes hidden behind dust. Some may be black hole stars caught during their brief, brilliant transition. Future observations will test these ideas. Webb can observe the same sources at additional wavelengths and search for changes in their brightness. A compact accretion-powered object may vary more rapidly than a galaxy filled with billions of ordinary stars. Astronomers can also look for broad emission lines, hot dust, and the chemical fingerprints expected from intense ultraviolet radiation. If the central engine is powerful enough, it may carve out ionized regions around the object, creating a recognizable spectral signature. Other observatories will add another piece of the puzzle. X-ray telescopes can search for high-energy emission from the accretion disk. Radio arrays can look for jets. Gravitational wave detectors may eventually sense the mergers of the massive black holes that these early seeds become. There is an almost poetic twist here. The object may look like the oldest kind of thing in the universe, a star. Yet hidden inside could be the beginning of a galactic black hole, an object associated with the universe's most extreme future. And because we see it across such a vast distance, we are not seeing what it looks like today. We are seeing an ancient moment preserved in light. The telescope is not merely looking farther away. It is looking backward through time, toward an era when the first structures were still taking shape. The discovery also reminds us how much classification depends on perspective. Up close, the system might contain a black hole, a disk, a cocoon, and outflowing gas. From billions of light years away, all of that complexity collapses into a single faint red point. In that sense, every distant object is a message encoded in light. Its brightness tells us about energy. Its color tells us about distance and dust. Its spectral lines tell us about atoms. Its shape tells us about scale. The science comes from assembling those clues without forcing them to say more than they can. For now, the black hole star remains a compelling hypothesis supported by a growing set of observations. It is not a replacement for every explanation of the early universe. It is a new possibility that makes the cosmic timeline more flexible, and perhaps more surprising. The James Webb Space Telescope was built to study the first galaxies, but discoveries like this show that the early universe may not fit neatly into familiar categories. Stars may have hidden black holes. Black holes may have helped build the first galaxies. And objects that look simple may contain entire stages of cosmic evolution within them. The next time you see a tiny red dot in a web image, remember that it may not be small in any ordinary sense. It could be a furnace, a cocoon, a growing black hole, or a brief bridge between the first stars and the first galaxies. Somewhere in that ancient darkness, a star may have been becoming a black hole while still shining like one. And across 13 billion years, its light has finally reached us. This is the quiet cosmos. Subscribe for more journeys through the strange, beautiful, and still unfinished story of the universe.